Alright, time for another draft physics, or science, video presentation, pretty much. So I'm going to read some quotes from Einstein and just use them as talking points and attempt to explain, why this tunnel vision, this blinder vision of science, just leads to this, just doesn't get off the ground kind of thing, because everything has to be viewed through the lens of just a few minds. There's just a few people who become the icons, and everything has to go through their lenses. And it's just pretty destructive to possibilities, but so much is just ignored and overlooked and not seen and not analyzed and not appreciated and all that kind of crap. That's a real downside to the process, because what the process really is that we've collected all these facts, all these experiments that indicate something. There's a cause and an effect, and if we're careful, we can glean some information anyway. You glean information from each experiment, and all of those facts need to sort of be put into an order, constructed, and there what everything has to be seen through, the lens of the facts. And so what I'm sort of saying is these individual minds have, one of them has this clump of facts, and another guy has this clump of facts, and another guy has, but nobody has all of them. And there's kind of no obligation, to go through a coherent filter. The filter is always the little brick walls that each person puts up because of how they've constructed their viewpoint. And it's not a filtering process that makes the getting to the conclusion more efficient. It makes it less efficient. It blocks more, it kills more babies than it filters out bathwater. Is what I'm saying. And that's part of, and you now, especially just because of the way people are able to communicate, it should be less of a problem. Just because of the fact that it's so easy to have the conversations. And but there's always this thing in the way too, of that everybody's has a personal ownership stake. I said it first, I thought of it first. I mean, all of this precedent idea gets in the way too, where everybody's competing to be the guy who thought of it, or the inventor, or the to get recognition. And so they're all restrained from having real conversations with each other because they don't want to give away any secrets that might be useful in terms of them claiming ownership. And so that just makes it even messier. And then you have all the personal ego crap, and people start to end up hating each other, and so then they hate each other's ideas. It's just really a mess. But anyway, so these are some quotes of Einstein's from different points, and I just found it curious. I was reading it, and then I watched another one of the Kathy Loves History, Physics, or whatever videos, and the same thing came up, and it was kind of funny that, it's a revolutionary idea, supposedly, yet I never even heard it. So it's just kind of funny that it's never a talking point, but yet it was supposed to be a revolutionary point or a key point in history and all this kind of stuff. But anyway, so we'll just go through some of this. I mean, the point is that in 1905, Einstein said something that's pretty revolutionary in sense of understanding photons. And by 1909, or 1911, he'd kind of been just driven away from it by the lack of interest anybody had in that conversation, and probably some points where he couldn't find continuity between this new view and the experiments as he understood them. And that's the key point here, is as he understood them. Like the two-slit experiment or something. You can understand if you believe what they say happens, in terms of like when they claim a light spot gets dark. if you believe them that that actually happens, then you're stuck because your theory won't be able to account for the results because you've believed what they said happens even though they never demonstrated it to happen. like when they say they did a detector experiment or some other thing and they didn't really do it. That skews how people model things because they think an experiment is valid when it's really not. So it's kind of like I could go all the way back to the 1700s and the clay experiments, that demonstrated that twice the velocity equaled 4 times the depth in the clay. When that looks impressive, but you have to be a chemist and you have to understand that maybe clay isn't a very good way to test how much energy something happens because maybe it has a bias for things that move fast. Maybe its elasticity is completely dependent on velocity, and the faster you go, the more you cheat the clay. But there was nobody there to say that. So if you believe that experiment was good, it's like the ferrocell, right? I mean, it's really powerful as a image. It's powerful as an overt statement. You're seeing light bending. It's doing it. It's pathways of light are bending, and it looks, if I gave it to a kid, who doesn't know anything, he's going to be fooled. Okay, there's no doubt about it. It's going to be he's going to think light is traveling on those paths, and he's going to draw these conclusions. It's going to look like fiber optics, even like these are pathways. He's not going to understand that now what's underlying that is just an illusionary image of light reflecting, that you're not even seeing the path of the light. You're just seeing points that light's reflecting off of, and you're being deceived, okay, because of the glass and because of all these circumstances. You're getting a fake image of reality. But I'm just saying that obviously that can create an illusion that's powerful in terms of having a very false impression of the actual facts. So even collecting what are the actual facts can be difficult when there's people saying, people who have looked at magnetism through years of iron filings and other experiments demonstrating this certain pressure and all this kind of stuff and how things react, and somebody whose impression is based on the fact that they've only looked at it through ferrocells. I mean, they're going to have a completely different lens to look at the facts with. All right, that was an awful lot of a premise. But when I get back to Einstein again, so part of these states, I'll identify which are which, but I mean, part of them are written, 1905, and part of them are written sometime later. And he doesn't write much later about photons that I've been able to find so far. But I haven't gone through all the later writings. And unfortunately, his statements are very concise. I mean, he doesn't do any elaboration, and go into any details at all, which is really unfortunate, because that's where all these misimpressions come from. But anyway, so in 1905, he is saying something revolutionary, and by 1911, he's starting to turn it back into something that fits with the conventional notions. So I'm not saying he's completely departed from this thing, but he's wave particling again. He's starting to say it's not about waves or particles. Now it's wavicles or particles, waves, whatever. And that's sort of disappointing because he was so close, and from my perspective, from my viewpoint, he obviously came to the same conclusion I came to. Okay, I didn't come to it because Einstein wrote it. Obviously, I didn't read any of this before I came to it. And yes, it can only work if you go through these experiments and figure out why they're saying something that's completely incompatible, and it might not be because the experiment actually said that. All right, anyway, that's the point I want to make. So you have roadblocks that are put in your way, like the ferrocell, or like two-slit nonsense, that make a theory seem impossible. when no, it isn't impossible. That evidence wasn't real facts. Okay. All right. So he says, I have already attempted to show that the present principles of the theory of radiation must be abandoned. So although he also made statements saying, well, it's a great theory, this wave thing, blah 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 blah. Yeah, he's clearly and overtly kind of trying to get people to just stop thinking of waves and start thinking in terms of particles and quanta. Newton's emission theory of light seems to contain more truth with respect to this point than the oscillation theory sense. So, I mean, it's not a hard statement. He's trying to just, it seems better, First of all, the energy given to a light particle is not scattered over infinite space. So he's bringing up some of these points that, the wave people have never dealt with, this infinite energy, in the sense that somehow these waves have to retain a consistent amount of energy, over endless amounts of time, spreading over endless amounts of distance. And that doesn't make any sense as just an energy theory. It fails. All right. First of all, the energy given to light particle is not scattered over infinite space. So clearly he's getting the point, the idea that a wave theory just breaks down because it really is an infinite energy theory. It has to keep making more and more energy because there's no way the tiny amount of energy could spread over all this infinite space. But this infinite from our point of view, infinite compared to the amount of energy. It doesn't have to be infinite, it just has to be, you could use a less dramatic word, this immense space, but remains available for all elementary processes of absorption. So it's clear that the process of absorption is always the same whether you're 10 million miles away or you're right next to it. The absorption is exactly the same. It just doesn't make any sense that there's some spreading force that's able to produce that result. Okay, so this is just a nice statement of Einstein pleading with the world to have a rational conversation, and obviously he failed. No one listened to him. Anyway, nevertheless, with respect to the question, I believe we stand at the beginning of the development of the greatest importance that cannot yet be surveyed. I mean, he's obviously in this moment he's thinking, this is, huge. I mean, it's a gigantic switch in perception. He's not talking about wave particling. He's not talking about some slight modification. That this is, a complete turn, not just some, let's go 10 degrees to the left of the wave theory. The statements that follow are largely my personal opinion, are the results of considerations that I have not yet checked through others. So, he's being as careful as he can not to offend anybody, not to say, don't call me a flat earther, please. I'm speculating, these are thoughts, and I just think it's a conversation that needs to happen, and yet it hasn't happened yet. I really can't find anybody to talk to, he's almost saying. I haven't checked enough not checked enough by others. He's sort of indicating that I'm not getting any feedback. Okay, if I present them here in spite of their uncertainty, the reason is not an excessive faith. So, technical issue, should be back. Sorry. All right. The statement that follows largely my personal opinion. Okay. Considerations I have not checked through others. If I present them here in spite of their uncertainty, the reason is not an excessive faith in my views, but rather the hope to induce one or another of you to deal with the questions considered. So it's kind of funny. He's writing this as a paper, a real submitted scientific journal paper, and it's basically a plea that maybe we should talk about the facts about what a photon is, before we project larger theories on top of things that really aren't consistent, that just don't make any sense. And it's just funny that he had to do that in the first place, but that that he can't find the conversation or provoke it, and that he has to do it in such a formal way. But it clearly indicates that any other scientist who works of, that's almost impossible to provoke the conversation among the people who have the power to dictate conversation. Yeah. All right. So this is the important statement. So this is in 1905, the miracle year, blah, 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 blah. Light can be better understood on the assumption that the energy of light is distributed discontinually in space. So that it's not some wave flying through space, that it's some sort of stuff that is separated by nothing, almost, it's sort of saying. According to the assumption considered here, when a light ray starting from a point is propagated, the energy is not continually distributed over an ever-increasing volume, but it consists of a finite number of energy quanta. So, localized in space, which move without being divided. So this is where it's just one little sentence, and it just needs to be a little bit more than that to make that understandable by anybody reading it. Okay, but he's basically just saying exactly what I'm trying to say, is that a photon is a composite object. It's made of quanta. The photon isn't a quanta. What's inside the photon is quanta, separated by distance. Okay, localized in space, which is kind of funny for Einstein, right? Because he doesn't think there is such a thing. But he's clearly, back to three-dimensional space and pretty much saying that each bit of quanta has its place in the universe and is moving in a direction. And that the quanta, the frequency, which he doesn't mention, is the distance between the quanta. All right. A finite number of energy quanta. The finite part clearly meaning this is a ray, okay, the quanta are moving in space, and they are, the frequency you could just deduce must be the distance between the quanta. Okay, which move without being divided. So the point is they're not separating, and they're not going in different directions. They're all going in the same direction. And they don't break into pieces or subquanta or any of that kind of stuff, and which can be absorbed or emitted only as a whole. Now he's not talking about the whole photon, he's talking about the quanta. The quanta can only be absorbed as one piece of quanta. It either hits you or it doesn't hit you. So anyway, but that's, it's a small statement, but it's gigantic in terms of he did get it. Okay, he was asserting that a photon is a composite object made of subparticles, called these quanta. So that's the first time the word's used, energy quanta, and clearly what it's saying is the whole photon isn't an energy quanta. The photon is made of quanta. All right. So, and this other statement, I think, is in the same paper. The simplest picture is that a light quantum transfers all of its energy to a single electron. So this is a sort of a different subject, in the sense that now we're talking about how do you get an electron to move, or how does it get kicked out, or what's the process of absorption? And I guess this would go back to the process of emission. But anyway, all of its energy to a single electron. So the problem with that theory is that a photon, see, if all the facts were put into the picture of, a photon has this huge polarization. So we know that the quanta is filling more than space in the direction it's moving. It's also filling, in a sense, space in a polarization, and that polarization clearly can't hit a single electron. But what we have in experiments is all we can see is the single electrons moving. So, did a single piece of quanta make the electron move, or is there something more happening? And my obvious argument is there has to be more to the story, because a single quanta isn't going to eject an electron. All right. We must, however, not exclude. Let's see. Well, I just read that again. The simplest picture is that a light quantum transfers all of its energy to a single electron. So this is just saying that the quantum doesn't break into pieces. It either hits an electron or it doesn't. So that's just a simple question of the bit hits the electron. Now why does the electron move? One time pops out, another time doesn't. Now we're back to frequency, and how do you get more than one quanta of energy to hit the same electron is the real argument. Okay, we must, however, not exclude the possibility that electrons only receive part of the energy from light quanta. So then it's a concession that, well, how are we going to explain what's happening? Because it's clearly there has to be something else there, because the electrons behave differently depending on the intensity of the light or the intensity of the quanta frequency. But again, he never says the word frequency. He never talks about the polarization. So it's just so little that you can't really. So I guess part of the reason why there was no conversation is that he didn't say enough about the evidence and the features. Now, he did say a whole bunch in the paper about black body radiation, and but it didn't say anything. That's all mathematical, probability study math, to define why, you can't create gamma rays as easily as you can create, red light. So that was a much more complicated and mathematical argument that sort of distracted from this key point he's making, is that the black body radiation experiments and the cathode ray experiments were sort of demonstrating, the photoelectric effect, that this wave theory just doesn't work, and that you have to understand that there is a clumpiness to how energy moves through this system, and it's just not going to work to say it's some sort of wave function, some sort of wave push. Because a wave push, you can't cut it into on and off, and it appears that on and off is what's causing the effect. You either hit it or you don't hit it with a clump of energy. Alright, well that's... don't know if I did that exactly the way I wanted to, but it's close enough. So the rest of the video will be me attempting to throw a few facts together that I just thought, would make the conversation even more interesting, because these are all things they knew in 1905. So in 1905, they knew pretty well that gravity, that the electric and magnetic force, whatever you want to call that, I call it just magnetism or charge, and light all travel at the same speed. So already in 1905, they knew they should have been saying speed of force, because all of these things, all these invisible action at a distance mechanisms, all of them had the same speed. So there's good reason to think whatever they are, they all have to be explained with some material function that's going to be the same. It would be kind of strange that something like bent space and very different things, and then charge and then gravity would all be separate evolutions that just happen to have the same speed. Very separate mechanisms, very different, distinct mechanisms, all having the same speed. So that I think should have occurred to Einstein to say, well, we probably should be. Well, he did. He was spending his whole life trying to unify these three forces. These mechanisms. But he just didn't. I don't think I don't think he explained the foundation for that unification based on that simple premise, and that you could quantize gravity as long as you have a mechanism for it. There's no problem. I mean, so I've given, there was some comments in the comments section. Some snarky guy was telling me how it's impossible, this, that, and the other thing. And I gave him the simple scenario. Well, let's just change the scenario of gravity. Let's just imagine gravity as grains of sand, okay, and moving down towards the Earth, okay, and they're moving in a sense, in a way, from different locations in space, okay. And now this part I didn't add when I was saying it to him. So they're consolidating. As you get closer to the surface, more of it's going to hit you, because it's getting, the grains themselves are getting closer and closer to each other. Okay, they're contracting as they're moving towards you. They're contracting, so more and more of it hits you the closer you get to the ground. And they have a velocity. So they have both things. They have a velocity towards you, and they are consolidating as you move towards the center. If you get closer to the center of the Earth, more of it's going to hit you. Just as you get closer to a light bulb, more of the photons hit you. Same rules apply. So the further away you go, the less of it hits you. You know, in the inverse to a light bulb, the more you move into gravity, the less gravity there is. You know, ironically. So if it was grains of sand, and then we just did a simple trick where we just said that, you know, if you have mass, it means you have the same proportional to your mass as your surface area exposed to the sand. You know, so I could take the feather has very little mass, so it would have a very small surface to collect sand on, and if it's a heavy mass, then it's collecting a lot of sand. You know, and with those simple rules, just mock, you know, gravity. Just say, well, how does that model not fit with what we see? How is it different? You know, and then you can get into questions about whether you're moving into it or moving out of it. Now, that just has to do with how fast it's moving. The faster the sand's moving, the less relevant how fast you're moving, how much distance you change will matter less and less the faster it's moving. So obviously this light is moving very fast, so little tiny changes in your distance won't matter much in terms of how many soldiers you hit. You know, the more, like I said, more soldiers coming at you, the more distance you move forward into the soldiers, the less it's going to be a percentage of soldiers you hit. It'll be a smaller and smaller percentage of that. Yeah, the effect isn't dramatic. But anyway, so what else do I want to say about that? So I'm just saying you can, you know, say, okay, let's just create that scenario. Let's create an understanding, and let's say what happens then when you push into the, you know, you push up, you know, into this stuff, or you're falling with it, or all, and are there any facts about what we observe with gravity that indicate that can't be true, that type of scenario isn't the right answer? And I'd say there aren't any, okay, because gravity is actually a force that carries momentum, so it's just like a grain of sand. It has momentum. Now, what it doesn't have is, you know, the point is you wouldn't collect the sand. That is, you wouldn't collect a big pile of sand on top of you. Obviously, photons don't have any, I have to carry them, mass. Okay, there's none of that involved. Alright, so where else do I want to go? Okay, so I'm just saying, so you know, we have these sets of these facts that tell us, okay, they're all moving all the forces have the same speed, and it's, you know, hugely important. And all we're really saying is that, okay, we know the photon, you know, we've just decided, okay, so let's just say that quanta exists. And so a photon is the stuff moving the speed of light, and what we know is its key feature is it has a frequency. You know, there's a distance between them, and then it has something called polarization, which is basically telling us that through space these little bits aren't necessarily, they're traveling a path that's parallel, that doesn't change, the same exact direction, but they were fired from a slightly different location, so they're a little bit out of alignment, so it has this polarization. You know, that could be 500 atoms worth. It's not a small amount. It's proportional to the frequency. So whatever their frequency is, that's likely going to be the polarization. And we don't know how many there are. There could just be two, you know, one here and one here. And now the key point is going to be is how does the matter interpret that? How does the matter know this distance? Because one electron certainly can't receive this stuff happening over atoms worth of space, so the same photon can't be doing the work. And now you can say, well, there's a whole bunch of these photons, so one hits and then the electron, and then another one hits the electron at the right moment. And I'd say yes, that's part of a rational conclusion, but there's lots of ways you can set it up so you understand what the catch is. You know, like I said, I can give you an analogy, okay, to actual waves, and point out that when something goes straight into the water, it's basically converting energy going this way, you know, into energy going that way. And it's all of the energy is going to be converted, so there's no loss to anything. It'll all go that way eventually. You know, and it's saying I'll take a high amount of energy here and I'll spread it into a lesser amount of energy going in all these directions. But it's the same amount of energy. If 10 went in, then this is all 1, 1, 1, 1, 1, 1, 1, 1, 1. You know, you're just taking energy going this way and you're just turning it into energy going that way. And the same theory, like say if a photon, the first bit hit here, the energy, okay, is less, but it's going this way. You know, it's all the electrons. You hit this atom and all the atoms next to it, all their electrons move a much slower speed, much less velocity this way. And then this other second bit of the photon now that's you know, come in and it's got a certain distance between it. Well, the distance just happens to be exactly the distance of this traveling distance. So when it hits, whether it hits here or it hits here or it hits here or it hits here, it doesn't matter where it hits, but if it hits here, now it's going to take that one velocity, which is a real velocity. Okay, it's a lot less than the 10, but it's a real velocity. And now it's going to add to it. So the thing is already moving this way, and now it's going to hit again right behind it and push it again. And that's the extra that makes it possible for the electron to create enough instability in the atom where now an electron is going to be ejected. Now we have to talk about the speed at which the electron ejects, because we know from, so this is where you have to just add up all these facts. I mean, we know from the fact that there's a spectrum, that is, certain frequencies will be created of light. Well, the frequencies are sort of telling you that there's a certain amount of energy that the electron moved at, you know, a certain speed, that it was able to create photons of a certain distance when it moved. And so how's it creating those photons? Well, if you believe, you know, that the whole system is constantly being bombarded, that is, an electron sitting here is all the time being hit by quanta. And the fact is that in most circumstances it's been, you know, it's just being hit by the same amount from every direction, everything's fine. Now if I put it in gravity, you know, well, there's a few extra ones coming down this way. And so the electron will move this way. Okay, I'll have a velocity that way because the force is going to be pushing it that way. And then I could blow wind this way and blow the whole atom, and that also makes the electron move, and so it moves this way. And of course it could be jostled around a lot of directions, but it's always going to have a net direction. There's always going to be a net position it's going to end up in based on all the forces that are affecting it. And the electron's completely indifferent. It couldn't care less. It's just going to go where the net force tells it to go. So the atom collects, you know, momentum, so to speak. What it's really doing is just going where the force is telling it to go. All right. Well, it's a little more complicated, because the nucleus can store the energy, and it can store energy in a direction. And that's really what you're doing. When you're accelerating something, you're taking that force and you're basically making it permanent. Okay, you're making it permanent in the sense that you're creating a circumstance inside the nucleus with the electrons and protons that enables the energy to keep pushing in a direction. And well, I don't want to, that's the more complex thing, so I don't want to really go there yet. So where was I? So the forces, gravity. Oh, okay. So if it's in a place where it's constantly being hit by energy, you can, and I've done this so many times. If I move my hand towards you, more light hits you, more photons. I reflect more photons, okay, per second. If I move away from you, I reflect fewer photons per second. And the size of my hand, as you see, gets smaller, which makes it even harder for me to reflect light to you, because less percentage of all the angles are now hitting you. Okay, here I increase that all the angles hit you, more angles hit you. Here, fewer angles hit you. There's more angles that are missing you now. So the closer I get, the smaller the cone gets that you can see. So the closer I get, the larger the cone. The further away I get, the less percent of the cone you can see. So anyway, it's and the same thing. The electrons are living in the same universe. They're in a position. They're getting hit with stuff all the time. Now, if I move the electron, what I'm going to do is move it into all of this force, and so if I move it this way, make that clear, and I'm moving it away from all of this force. So this force can't possibly reflect as much because this is moving away from it, right? And the faster it moves away from it, the more this force can't hit it. All the way to the point where if this is moving close to the speed of light, then nothing's reflecting, and essentially the electron is becoming invisible from anybody attempting to receive radiation from that direction, the direction the electron's going. I'm not going to receive any radiation indicating an electron's there. In the direction I'm moving into the force, while I'm collecting it, I keep reflecting it, reflecting it, reflecting it. But if I'm going very, very fast, it's not getting too far ahead of me. Okay, so what I'm doing is taking energy that was in this space, and I'm cutting it down to energy in this space. So you can understand if the 10 little things have to be in this space, all right, or you have 10 things in this much bigger space, that's almost like Morse code. That's almost like saying this is a dot, and this is a dash, and a dot and a dash. You're turning it into a signal by just compressing how much energy is in the piece of space. So when an electron's moving, what it's really doing is creating, part of what you would call a photon, in the sense that it's clumping a bunch of this quanta, gravity. It's clumping the gravity, so to speak, the reflections. And when it does it a second time, as it keeps moving, it's clumping, all right, and that will end up being a photon, in the sense that it'll be a whole bunch of photons, in the sense that this is a photon, this is a photon, this is a photon, this is a photon. All the connected clumps are essentially photons. So one electron moving can create 500 photons. So the idea would be if an electron moves from an energy level, from in an atom, it's inside the atom, and it moves in high pressure, and it moves quickly out, right? Quickly to a new position. You can understand that what it's doing is and especially if it oscillates, let's not get into that. If it jumps back and forth, you could understand that from this perspective, it got compressed. From this perspective, this is the empty space. Okay, so when it went this way, it sent empty space this way, and it sent compressed quanta that way. And then if it goes back again, then it's going to send the compressed, is going to be sent here, and in this direction it's going to give you the empty. You see how simple that is? I mean, that's a pretty simple explanation, that a photon is just the energy of the field being compressed or having less density. because you're moving away from it. Very few elements ever reflect because you're moving away. So fewer reflect when you're moving away from the back end. So it's really creating two photons. The movement is essentially creating the constituent of two opposite photons, completely out of phase. Now that connects, obviously, to the entanglement experiments, where they use a crystal to create two photons, okay, that are completely 190 degrees out of phase. So, and that would be the explanation. And they're usually going in opposite directions, which also fits with those experiments. So it fits. I mean, I'm sure somebody could point out an experiment that maybe doesn't do something similar to this, but I'm just saying that I can counter-argue those experiments, and that's what I've done over these years. Is people brought up the two-slit experiment and this and that, and saying it's a conclusive phenomenon, and I've demonstrated where no, it's not conclusive at all, because much of it is mythology, much of it is just storytelling, and the real evidence doesn't indicate it's true at all. That there's no particle theory that can explain. So I've sort of explained that the theory would be is that the quanta, the little bits, are at a frequency, and what's really happening in the slit experiments is much of the light just goes straight through the middle of the slits, undisturbed. And the only light that's creating the fringes, the only light that's creating all this noise on the sides, is the light that traveled near the surface. And the light traveling near the surface, all surfaces have a bunch of electrons on them, all transitions between mediums. And we already know about diffraction and all that kind of crap, so clearly photons are going to get deflected, and all they have to do is scatter off of these points. Okay, so all we need is the quanta. One quanta hits here and it goes this way, one quanta hits here and goes that way, one quanta hits there and goes this way. It all gets scattered over the whole board, and all you have to do is figure out, well, where can they be reconnected, or where can the pattern be reconstructed? And there's always a point, where there's a high probability of reconstruction, and then at this point there's a low probability because these distances won't provide photons in the right order. They'll have photons that are too close to each other or photons that are too far from each other. And so the pieces won't be reconstructed back into the frequency. And therefore you won't see them as light because they won't have this consistent frequency that they need to be seen as a photon. And so that theory works, that model works. It explains the phenomenon. It also has the benefit of also explaining why this is brighter here in the center. It's brighter because the center is really an off. Okay, the center is really an off. Even though we know these are going to be the same path length, those are inside the distance of the whole experiment, which is only 1 millimeter. So the only time that those lines match is inside of 1 millimeter of distance. Outside of that 1 millimeter, they don't match. They're really destructive. They're really not reconstruction. They're not in phase. So outside of this tiny millimeter, they're out of phase here and here. The lines don't. The distances don't match a full wavelength of distance just outside of that millimeter. And so the center maxima is bigger because it's really two fringes that are so close together. And when the center light does hit that inside the millimeter light, well, that's the one filling this in. And the light that goes straight through. The light that goes straight through obviously is inside of 1 millimeter. But the laser spreads a little. And so it's just filling in this middle part. So you think it's one big blob. No, it's really two blobs, okay, and the middle's been filled in. All right. It's only two blobs. It's not three. There's not an off here. There's just not an on. It's not 100. It's not fully out of phase here. It's only that it's not in phase. The in phase is at some point here. It might be here, it might be here, and that really depends on this lines. These two lines are the full path length difference. You can't get more of a path length difference than here and here. So here at 90 degrees is where you see that how much are they really out of phase, and this will tell you. And so it starts with maybe half you only have half of a fringe here, and then the next fringe, and the next fringe, and the next fringe. Whatever it starts with here is what it's going to end with here. And so that's really telling the tale. And the center point is obviously half of this in terms of the total number of wavelength differences will be 50-50 here. Okay, half of them be on one side of that line, half on the other side of that line. So you could just do the math and say if there was 15.5 wavelengths of difference, that half of that would be another tricky number, 7.75. And that's still not a whole wavelength, clearly. Anyway, I didn't want to get into that stuff, actually. So all I guess I wanted to... So I just gave you a couple of the examples, how just understanding this as all of it is moving the same speed, and all of it can be understood as being quanta. And the part that gets a little tricky is charge, and I've already been over the fact that the answer to charge is just to understand that, yes, there's a subtle catch, that all of this force is actually two types of force. All right, just as there's an electron and a proton as elemental style particles, and I would argue they are, elemental. That quarks and all that kind of stuff is just kind of made up nonsense. But anyway, there's elemental force. So the force comes in the same two varieties. And all you're really saying is the two varieties interact inversely. So if I hit pink with blue, it just diverts. I hit pink on pink. The pink causes momentum in the electron. This piece of chalk's a piece of crap. And a reflection eventually. So the energy reflects eventually. When the electron stops moving, it'll certainly be reflected. There's no change in the direction. So 2 plus 2 plus 2 physics. Two kinds of force, two kinds of interaction, momentum and diversion. Two kinds of matter, then two kinds of interaction. So, simple enough. But anyway, I'm just saying all fits together, all can tie together, and it's so much simpler than the standard model. It's so much easier for me to draw it than any kind of wave that has polarization, and carries the same amount of energy to all points in space. I mean, you can't even draw any of their stuff. The bent space, you can't draw it in 3 dimensions, doesn't even work at all. It's impossible. But this works. And you just keep nice 3-dimensional space. All you have is momentum traveling through it. The little bits have the momentum. They're moving the speed of light. The bigger bits, the matter, doesn't have any of its own. Okay, it has to be forced to be going somewhere. The little bits have to force it to go somewhere. And that simple model works. It's not catastrophically flawed. It's not, it works. And it's so much simpler. And the conversation needs to happen in some sort of rational manner where it's not just flinging insults. These insults aren't a counter argument. They really aren't. Okay. So anyway, that's enough of a video, I think. Okay, yeah, so I'll hit this button. So this has been a DraftScience video presentation. Yeah, I'll say that. And I'll see you next time and such.